start. In the last class, we studied about about linear system and Gauss-Jordan elimination. How to be able to get the solution of some linear system, and by representing two augmented matrix, for a linear system, we define some operation in matrix, and I will generalize about what is matrix, and I will define matrix and the operation in this class, and I will solve some exercise, some examples, and I feedback my last class video, and my letters are fairly small in videos, so I will write more largely, more larger. I upload to YouTube, but it is not. No, it cannot see other people. I can just see, and if you want, I can send the link. Yeah. So if you want, I can give, and I'm not sure it is helpful for you. Okay, then we will start today's class. In last class we focused on linear equation, and today we will focus on the matrix. In the last time I introduced what is matrix, but I will explain one more. It might be not rigorous definition in matrix, but in this book, I think it is enough to understand what is matrix. I will write more larger. Matrix is an array of numbers, and this array is positioned in rectangular. So we define a matrix is a rectangular array. And in this array we have numbers, so we called it, which is called it entries of the matrix. And the matrix, the size of matrix is rectangular, so we might be written the size of matrix, and And so the size of matrix is the number of row and columns. So I will give an example. If you have this matrix, then it is rectangular array, so, and also it has 2 rows and 3 columns. So the size of matrix is 2 times 3. 2 times 3 matrix. And we usually say this 2 times 3 matrix or 2 by 3 matrix. And in the last class, we get the solution of some linear systems. And in the solution, the concept of solution is from equation. So we want to define the equations of matrix. Then we might need to the next definition. How we can get equal from matrix? It is to compare to two matrices. We might need to the concept of size to corresponding for each entry. So the definition is that two matrices to become equal, they have same size and their each entries are all same. So we get the what is equal. Then from this we want to construct its addition or multiplication like this system, because this class is linear algebra, and algebra has plus and minus and multiplication, plus and subtraction and multiplication. So we will construct their operations. First, I wanted to use this whiteboard also, but if the matrix is, for example, one matrix is 1, 1, 1, 1, 1, 1, and another matrix is 2, 2, 2, 2, 2, 2, then it is not equal, and I will define another operation which is called the scalar multiplication. So we can denote this by using this matrix, and it is like this form. By multiplication for each vectors, we can get this matrix. So it is not equal because yeah, right. But in the linear system, we might get same solution, and in this sense, of course, it is also have same solution. But from this, we might make another matrix too, like this. It is also have same solution, but it does not mean the linear system is same. The solution, it means the solution set is same, and it does not mean the matrix is same. So I defined the equal in the concept of matrix. Okay. So I will give arithmetic of matrix. First, let A be a matrix of size n by r matrix, and also let be a matrix, but its size its size also same. And let the third matrix C is CB m by n matrix. From this, I will define the summation and difference and scalar multiplication like this. And finally the product. So some A addition B is for its size is same, so there all entries can be corresponded from A to B. So each vector we will write I row and J's column. So each corresponded entries summation is A plus B, and similarly we will define subtraction, right, for corresponded entries. And scalar multiplication is similar to this, so we need a scalar For the scalar, we will define C times A is for each entry of Aij will be multiplied by C. And product is a little special because it defined it by its for each entries we will define like summation k from 1 to r, because A size is m times r and C size r times n. We will correspond each row and columns, and this process is called the row column rule, and the multiplication is real, same to real multiplication for each vectors bkj. And sometimes some people might ask why we need to multiplication from row and column, row by column, and this implies this might give associative rule, and it to calculate in algebraic system, it is very important, because if we do not have associative rule, then sometimes we cannot write for each matrices AI. We want to not this product like this, but in this formation if we do not have association rule, then we cannot return by this because it change this. So we should denote how which vector will be operated first. So the associative rule is very important in our arithmetic system. So why it satisfies the associative rule? Let me show that. If we want to get let's see, D and D is n times L. Then by the definition of this, it is also a matrix, and its size is r times n, so its size is m times n matrix, and D is n times L size matrix. So we will thank you for comments. Right. So I will product AC matrix. Ultimate AC matrix multiply to D, then by the definition, one from N, AC is I N, and these N J entries. And it is also matrix multiplication. So we, by the definition, we will write like this. L H R A I H C H N and multiply the D and J. And we know that in the scalar arithmetic system, we have associative rule, like for the scalar ABC. AB times C and equal to A times BC. So we denote this summation also like this: GHN times D and J, and by not N, K, we will summation K. I'm sorry. So by summation first K, it will be C D H J, and its H entries is satisfied this form, so it can be written like A C D. So entries of IJ entries of the matrix. So we changed the bracket from A with C to C with D, so it satisfied associative rule. And let me give some examples using these operations. Consider the situation given A (0 to 7 3 4 0) and B is -4 2 3 3 2 2 5 0 -4 1 -5, and C is 1 2 2 6 4 0 6 6 3. Then we can calculate the summation A plus B because each size is same, and by the definition we will sum for each vectors, then it will be like that: 5 2 3 4 3 5. And similarly we can get the difference A minus B, so we will A subtraction B, so we will operate 2 subtraction 4 and -1 subtraction 2. If we calculate like this, then we get this matrix. And scalar multiplication also, I will give on scalar. C is -2. Then it will be multiplied for each vector. Minus 2, 4, 0, minus 4, minus 14, minus 6, minus 8, 0. And the multiplication, this will be multiplied row by column. So yeah, C, large C is capital C is matrix. Yeah, I will multiply A and C matrix. Yeah, it has 4 entries in row and 4 entries in column. So we will multiply for each vectors and we will sum 4 times. Yeah. Then I will write only first vector 2.1 plus 1.2 plus 0.4 plus 3.6. If I calculate it, then it will be 2. And if you it is first and it is 1 entries. And you might calculate from this, then you get 1. You can calculate like this: -1 multiplication 1, addition 0 multiplication 2, something. And then our entries will return like this. And if you not familiar to calculate this multiplication of matrices, then I recommend to calculate yourself by yourself. As you can see, the multiplication of matrices is not easy. Its calculation is by just calculating addition and multiplication by doing addition and multiplication, but its amount of operation is too much. So sometimes we want to in the large matrix, we might want to divide more small matrix, and by calculating in small matrices, if we construct original matrix, then it might be more better operation, or make more better situation. So I will divide the matrix, some matrices. So it is called the submatrices, and let A be a M by N matrix. Then if we divide the matrix into smaller matrices, then there are 3 types of partition. First one is for submatrices. A11, it is not it does not mean entries. It is also matrices because its name is submatrices. To 1 and to 2. It is written like this. It is also matrices, so it can be written a rectangular arrays of numbers. So if matrix A is written A11, A12, A1, and by 1n. If we if we denote A like this, then this matrix means one R R prime n R prime 1 A R prime R. Then this is also a part of partitional matrix, and another vector is also will divide as a matrix. So this sentence means we divide the matrix as 4 submatrices. And the second is its row vectors. I explained what is vector. It is the size of column is 1. Row vectors are I. Then it means it divides as row of A. So A11 to A1n is first row, and there are second row, and there are all m rows. So we can divide the matrix like this as using the row of A, and similarly it can be partition. It can be parted into its column vectors. Ci, then it will be written A11, AM1. It is C1 and C2 to Cn, and it is also a kind of partitions of A. So if you try to make some submatrices in A, then it will be written like this. And from this, you might divide more because it is also matrix. And so we have all 3 kinds of submatrices. By using this, we can denote the matrix multiplication easier. We do not need to write summation A, I, K, B, K, J. It is also sometimes is useful, but usually we do not use this form because its operation is too large. And by using this form, especially row form or column form, we can denote it A as the row form of B, as the column form of D. B. I will write the size of A and B. Its size is n by R matrix and R by M matrix. Then A product B is can be written like this, and its mean is AB1. It is the first column vector, and AB2 like this, ABN, and it is also matrices, so column vectors, having column vectors. So by dividing this form, we can denote more easier. And also we divided B, and conversely we can divide A, because by the row column rules, and then it can be like this, and we calculate A1 rows and multiplication B, A2 rows multiplication B. Its result will be row vector, because row vector multiplication B is, the size is n by R product R by M matrix. Then it give a 1 by M matrix as a result, like this. We calculate that, then we get the form of A1 B, A2B, AMB. And by using this, especially this form, we will write matrix. But we can denote, we can give some concept of linear combination, which definition is that? And now we calculate, we wanted to get the solution of linear system, and it is very useful tool to write it and to get it more easier. So to give the reason, I will explain linear combination. Same size multiplication, same size matrices, and if we have scalar, then the form of summation 1 to R C I AI, this means C1 A1 plus C2 A2. We define scalar multiplication, so it is very will be well defined. CRAR, and this form is called it linear multiplication. Of A1 to AR and with coefficients C1 to CI. So here CIs are called the coefficients of the linear multiplication. So by using this, I said we can denote the matrix multiplication more easily, and I will give an example on the to represent the linear a linear system. Let me give an example. If we have the matrix minus 1, 3, 2, 1, 2, minus 3, 2, 1, minus 2, and 2 minus 1, 3, 1 minus 9, minus 3. This matrix multiplication means linear system because it is corresponded to if it is x, y, z, then its multiplication by multiplying this 3y plus 2z equal 1 in the first row, and similarly we get other linear equations. So it means minus 2, 3, that's minus 3. So it is linear system, and it is a matrix representation of this linear system. I explained what is linear. I'm sorry, it is combination. I explained about linear combination, and it is written like this form. To represent the linear system, we calculate row and column, but it is calculated by using this form. Then it will be calculate this and this and this form, and B the second matrix, and third it is not wait yeah, right, I will explain again. I'm sorry. It is multiplication by keep this form 1 or 3 times 1 matrix by calculating first entries of column vector and second entries and second column vector, because we multiply row and column, so each entries will multiply only first column, and second entries will be multiplied to second column, and finally the third column will be multiplied to third column. So we first multiply to them with them, and if we calculate the summation, of course we get same solution. So it is written another form, and we say that this form is linear combination because it is scalar multiplication and scalar products matrix plus scalar plus matrix, like this form. So we see one. Yeah. -3. Yeah. Plus 6. Yeah, right. It will be go to 1. Yeah. Because to edit, we should input the results to the same position. Okay. And so this form is a linear combination of column vectors. Column vectors is also matrix. So it is makes sense. No, it is not dependent. It is not only column vector. We to make linear combination form, then it can be multiplied to right side column vector, or for on matrix, if we calculate row vector of left side, then it will give another. It also can be written linear combination form. I will give an example of another one. And I also in the last class, it is a little hard to continue for over 2 hours this lecture, so I will lect 1 hour and 10 minutes, and we will take rest time. Maybe soon we will have wasting time. No, not now. The time we start at 11:30, and I will write 12:40, and we have take rest time 10 minutes. And finally we will let to PM. So yeah, okay. So I will give this example. If we have this matrix multiplication, then by calculating this, we will get one times 4 matrix, and if we calculate this, we get the matrix, the row column, row matrix. And also, if we calculate instead of this form, we can calculate like this, because the first entries will multiply to first row, only first row, so it can be written 1 4 1 4 3 plus 2 0 minus 1 3 1, because the second scalar will be multiply the second row, and then we get this. And by calculating this, it is same to this because we do not change any entries. This multiplication is also same to this. And if we verify it, then first entry is 4 plus to the right. Okay. 1 times 4 plus 2 times 0 plus 4 minus 2, then 4 0 minus 8 minus 4. Oh, I think I mistake some calculation. I may. I think it is wrong. Let me calculate it now. Minus 4, and the second entry is 1 times 1, 2 times minus 1 plus 4 times 7. 1 minus 2 plus. I'm making plus and minus. 27. Okay, thank you. And yeah, it is right. And the third entry is 1 times 4 plus 2 times 3, 4 times 5, then 4 plus 6 plus 20, then 13. I mistake just first entry. Yeah. Finally, 1 times 3. I calculate myself it when I made this like these lecture notes. Yeah, I'm weak in adding calculating. Okay, then we see the 3 matrix multiplication form. One is this, and you see this form and this form by calculating matrix and column and rows matrix multiplication to a matrix. So we see the 3 types, entry by entry, and row by column, and column by row, and we calculate the size of matrix by corresponding the number of rows and the number of columns. So to make n by n matrix, if we have a n by n matrix, then it might be written n times n matrix and 1 times n matrix. So it means n by 1, then column vector, and it means row vector. So I missed the written. row by column and column by column, because we calculate column. And finally, we might calculate column by row like this. And after we take rest time, I will explain about that. Okay, let's start again. Finally I explained the matrix might be written the column vector multiply row vector, because if we have a n by n matrix, then it will be written n by 1 column vector multiply 1 by n column vector, because its size is same, so it might make sense. Actually, this method is called the column row expansion of AB. If I will do matrix then matrix multiplication AB is written a linear combination form, as a linear combination form, because we might not make by using just one matrix. It does not have a lot of information in column vector and row vector. We have n n entries and n entries, but it has n times n entries, so we might not denote only just one matrix multiplication of columns of vectors. So, but however, it can be written by using column vectors of A and row vectors of B, and in fact it is written its notation is not good. So this form is called the column row expansion of AB. Actually, this form is very important, and we use the R matrix summation, but sometimes by choosing better column and rows, or by making new column and rows, we might make this matrix more less than R prime. Is R prime is less than R, then it also a kind of information of matrix, and it is very important concept. And it, after we learned about what is dimension and rank and linear transformation like this, then it can be written rank and we will study about that in chapter 4. When then I will explain more detail. Came back to original concept of matrix. I explained a little. So if we have a linear system, then it can be written by using matrix and vector. For n unknowns, for n equations with n unknowns, then it will be written like this. To 1 x1 to 2 x2 to n xn. Like this, we have m equations and variary and unknown. And 1 x1 a and 2 a, oh, not m, because we have m rows, yeah, m equations. Then this will correspond by using the matrix multiplication and summation and equal, like this form: a11, a12, a1m, a21, a22, a2m, am1, am2, amn. And by multiplying a vector x1, x2, xn, it is m by n matrix, and it is n by 1 column vector. Then the solution will be m by 1 column vector, and it is from the linear system we get from b1 to bm column vector. And it is written by using A, matrix A, product X equal vector B. By using this, we might give from real equation in real system in equation. If we think about 3x equal 2, then we calculate it by multiplying of coefficients for each side. We will get the solution x equal 2/3. And if we can calculate this in matrix system, then it will be more easier to find the solution set, like A inverse A times X B, A inverse B. From this, if we have this, then we will get the solution easily. Before I explain this operator inverse, it is our final goal in today's class. I will explain transpose. It is similar to inverse operator, but I think it is more easier operator than inverse. Because it does change the entries if we denote Aij, then Aji, but we will make another matrix. Yeah, row we change row and change row and column. So let in this form we do not need to having square matrix, because if it was n times n matrix, then by setting n times m we can get the matrix also. So we will get n by n matrix, rectangular matrix. It means all matrix can be operated transpose. And with entries Aij, it is 4 i's row and j's column. Then the transpose of A denoted A to the T. Sometimes it is written small t. I prefer to write large t. And it is defined as n by m matrix with entries Aji. It is makes sense. So it I will give an example. If A was A11, A12, A13, A14, I will give just 3 columns. There is 2 rows. 2, 2, 3, 3, 1, 3, 2, 3, 3. 4, 1, 4, 2, 4, 3. Then it is A is 4 by 3 matrix. Then the transpose will be 3 by 4 matrix, because we will change the row and column. It gives 1, 1, A1, 2, A1, 3, A2, 1, A2, 2, A2, 3. Similarly, we get another entries of 3 times 4 matrix. So just we transpose the matrix in this line. If we see the operator transpose, the following definition is a little special, which I will explain about trace, and it is the summation of diagonal entries. Why I said it is special is the diagonal entries in the matrix if if we assume the square matrix, the 3 times 3, A prime, then is A prime transpose, then its diagonal entries does not change it. The position also does not change it, and the number of the position are also not changed. So it might be an important information of matrix, the entry of diagonal. So in this sense, I will define a trace as the sum of diagonal entries. To explain the diagonal, because if A was 4 times 3 matrix, then we do not have. It is hard to say what is diagonal. So I will assume A is square. Then the trace of A is defined the sum of diagonal entries. Let me give an example. I think if you see if you see an example, then you can get what is this. For the matrix A, minus 1, 2, 1, 4, 2, 5, 2, minus 1, 7, minus 3, 7, 1. It is square matrix. A is square matrix, and then the trace which trace A. So if we denote the notation trace A, then trace A is summation of all diagonal entries, 1 minus 1 plus 5 plus 7 plus 0 is 11. It is trace. It is simple and it is very crucial information in matrix, because we just learn transpose as the other operator. In this operator, it does not change the value of trace. So some invariant will give the information of matrix. Let's enter the inverse. And some algebraic property. We defined plus for addition, subtraction, and multiplication, and we see the associativity of multiplication, and I will note that the properties of operations. I think there are many properties, and I will give. These are very important in making equation or solving some equation. The plus, the addition is defined for each coefficient. So if we calculate a plus b and a, then it is then to b plus a because the in a matrix, yeah. Our matrix is and I assume that the following operations were performed. In this sense, the size of A and B matrices is same, and the associative rule is satisfied in plus in addition, and of course we saw that matrix multiplication can be matrix multiplication has associativity, and also by calculating this matrix, then it can have distribution rule. You calculating by assigning entries, you can get this property. I think if I write all things, then it takes a lot of time, so I will skip the proof. Of course, it is also the right distribution rule is also satisfied, and plus and minus also have associative rule because in the scalar in the entry case in the entry perspective, it is plus and minus is not different, and also is f and EFG. Scalar multiplication is more easier than show it because it will be multiplied to for each entries. So and the addition is also operated for each entries. So it makes sense, and plus and minus also is same. This distribution rule is satisfied. Right. In scalar multiplication, the right distribution rule is also satisfied. Finally, the associativity A, B, C is also satisfy this and ABC. ABC is and small a, small b, small c. Did I use c? No. Or scalar. And it is also satisfied if you have some doubt. If you are doubtful for that, then I want to check: is it make it or do it make sense? And I think if the perform the inverse, we should careful to 0, because in the scalar case, if we have 0, this form, its equation is right, but by dividing 0, it is not make sense. We have 1 equal 2, but it is wrong. So we should be careful for 0, and it is in matrix sense, or it is also important what is 0. So I will define what is 0, and it is simple. All entries are 0, then we will say 0 matrix. A matrix whose entries are all 0. This matrix is called a 0 matrix. But it does not mean except 0 matrix we can divide always, because if I give an example, a simple example, 1 0 2 0, for this matrix we want to get the inverse matrix of A, so we want to define A inverse. It is not 0 matrix because there is non-zero entries, but we assume that there is an inverse matrix of A. Then to calculate it, makes sense. It might be 2 by 2 matrix. Then I will write reverse A inverse A B C D 1 0 2 0. Then it will makes calculating this A plus 2B and calculating this C plus 2D, but this column is, the second column is all 0, so it will give 0 and 0. Then it do not want to say some identity in matrix. I didn't explain what is identity, but we do not want to this form, because we at least we want to get all entries and or column have some values. I might explain more later, but it is very important in metrics. So, so this geometrics does not mean except these metrics we can divide, and I will the answer how metrics we can get the inverse matrix in this class in this class after. And I give some property of geometrics. It is also fairly easy concept, similar to this property, zero matrix. Of course, all entries these are zero, so if although we plus zero means zero matrix. And having same size with A, or in this zero matrix, I will give proper size. It does not change the matrix, and the minus case is also same. And if we subtraction the same matrix, then it will give 0. It means there is an inverse element. In an additional operator case, in additional operator perspective, we have inverse element of A, and we calculate a small matrix, but if has 0 entry, then it will give 0. If A has 0 column, then the column's result will be 0. Whether it does not depend on the multiplying matrix, and if any matrix we multiplied, although we multiply any matrix, we get the 0 column from A. So if we multiply 0 to A, then it will be 0 matrix. And also, if a scalar multiplication CA equals 0, then it means C equals 0 or A equals 0 matrix, because to be 0, all entries should be 0. So there is two kinds of the answer. But that does not mean if we multiply, if we calculate two matrices A and B, if it is 0, then it is not true the following statements. if we multiply two zero matrix, then that means that should satisfy the D property. So 0 multiplied 0 is also 0. Remark means remark means if the result of matrix multiplication is 0, then it one of the two matrices is 0, but it is not true because okay, I make example, the counter example. It's 0, yeah. It doesn't mean at least 1 is 0. Yeah, okay. It's important information, so I will give counter example. If A is 1, 2, 0, 0, and B is 3, 7, 0, 0, like this form, it is not 0 matrix, but if we calculate this, then we will get is it right? Oh, I think it's wrong. Oh, I mistake. Then if we calculate it, yeah, right. It is not 0. No, they are not 0, but the multiplication is 0. No, however. And there are another remark. One is, it is also not true if AB equal AC for non-zero A. Because I explained in scalar sense 0.1 equals 0.2, but 1 is not equal to 2. So it is makes sense in matrix multiplication too. And I explained an example to find the inverse element A inverse for about 1, 2, 0, 0. But I explained that there was not like A's inverse, and we want to get the form of this, and how matrix we will get on matrix, and it is a little special matrix, and I will define what we want, and it means in the scalar sense 1 dot C or 1 dot for scalars 1 dot C equals C, and it does 1 does not change the C, and also if C is not non-zero, then C times C to the minus 1 will be 1. We want to do sense in matrix also, so I will define identity of matrix. it is divided in square matrix because if we calculate A for n by n matrix A, calculate some matrix inverse, it's wait, it is not good explanation. The identity matrix can we want to satisfy this form, then if we give some matrix C and we want to multiply the identity matrix, then its solution is also have same matrix, and I assume that the C matrix size is n by n. Then make this matrix, we should multiply n by m matrix to make n by n matrix. So in this sense, I will define the identity matrix as square matrix. So square matrix is called the identity matrix. If the diagonal entries is all zero, or all diagonal entries are 1 and another entries are all 0. So if I give an example, then usually we write the square matrix size, the size of square matrix n by n, so we need just one information. If we give one information of the number of column or rows, then we get another column, row or column. So we will read the number of columns sub of the matrix. So there are some example of identity, and these will be formed like this. All diagonal entries is 0 or 0, and another one is 1, and another entries are 0. Of course, we have 1 by 1 matrix. We have an identity in 1 by 1 matrix. And from this identity's definition of identity, we will define inverse of matrix. However, I said some matrices does not have inverse, so we should define what matrix is invertible. So I will define it. I will assume A is a square matrix think it is not needed to be square matrix, but I will give square matrix, and also, and if there are some matrix B with same size of A, such that A B equal B A's identity, because we want to corresponding to scalar sense. So in the scalar sense, we invertible means in scalar sense, invertible means does not zero. It is same statement, but it can be written another way. For scalar A, there is scalar B and satisfies this, and this means B is not zero. It's same, but geometric in the matrix case, although B is not zero matrix, we have another non-invertible matrix, so we will define this form. Then we say A is invertible. Or it is say non-singular, and it is more geometrical term. I will explain a little about singular. We will, after in this case, I will define the determinant of A, and it is I will explain it in chapter 2 more detail. It is a function, and it is fairly geometrical function because it is continuous map. So from this map, it is polar. If the determinant became 0, then A is not invertible, will be not invertible. Then the invertible matrix will come, this is if and only if. Then if A is invertible, then the determinant will not be 0. It is came from all elements except 0 in real number. Then this situation in geometry we say non-singular. Conversely, if there is no B like this, then we say A is singular. Singular is come from a point of continuous map. Of course, from this definition we can see the facts. If A is B is 1, then we defined A is invertible, and also B is invertible because by changing this side it doesn't matter although we write this form. So invertible, if AB is identity, then A is invertible and B is also invertible. And as a theorem, in the scalar sense, we have only one inverse element, so we might want to having same concept in matrix also. And this theorem says the concept of uniqueness. So let B and C be both invertible of A, invertible matrix of A, then AB equal I, and also it means CA is also equal to I. From this property, I will prove the theorem. This is a matrix, and when we define identity matrix by multiplying identity matrix, it is same, and also C is inverse matrix, invertible matrix, or inverse matrix of A, so it can be written A times C. I write conversely EA and AC. It also makes sense. So by calculating first BA, we get identity, and identity matrix does not change the matrix. So we get B equals C. This means there is only one invertible matrix of A. So finally, not this final. I want to explain determinant in 2x2 matrix. So I give a spoiler that if the determinant is 0, then the matrix are not invertible. Or from this concept, we will define the determinant map of matrix, 2x2 matrix. So I will give a matrix A, B, C, D. The matrix is invertible if and only if AD minus BC equal non-zero, and furthermore, A inverse matrix of A will be written AD minus BC 1 over AD minus BC D minus B minus C A. If we have this formula, then it will give more easy calculation. And it is developed in 19th century, mid term of 19th century, by Kelly. Kelly. How do you like? Yeah, maybe he's same people, same person. If I do not wrong, if I not wrong. Before I think I might keep this this probe, because I will explain more chapter. In chapter 2, I will explain the determinants. So when then I will prove this together. Let me give an example. You might have doubt from this, so I will give an example. If A is a matrix with entries 6, 1, 5, 2, then from this theorem, I will say this determinant A. Just we in this time we just use determinant in 2 by 2 matrix only. So in this sense, the determinant of A is AD minus BC. So 6 times 2 minus 1 times 4, 1 times 5 is 7. So it is not 0. Then it is invertible, and it will give the answer of the invertible matrix 6. And that's 6, 2. 2 minus 2 minus 5 minus 6. And if we try to calculate A, product A multiply A inverse, 6, 1, 5, 2, 1 over 2 over 7 minus 1 over 7 minus 5 over 7, 6 over 7. Then in the first entry, 6 times 7, 2 minus, what is it, 5 over 7, then it is 1. And the second entry is, if we calculate it, 1 plus, what is it? Oh no, not 1. We will calculate this. And 1 plus 6 over 7, then it will be 0. And third entry is plus 2 minus 5 over 7 is 0. And finally, 5 dot 1 over 7 plus 2 6 over 7 is 1. So we get identity matrix. And if you try to calculate A inverse A, then it is also give identity matrix. So we saw just one example, but if you try to another example, then you can get the inverse matrix and you can check it is true. So we now know what is inverse. So I will give some property of inverse matrix. I will write simply. AB are matrices, and it is. I will give square matrix because to be invertible, it should be square. So, as a brief note, if you give non-square matrix, then we might have question why we should give square matrix, because if we have n by n matrix, and by calculating n by n matrix also can have identity, and also conversely n by n multiplying n by n, it is also give square identity matrix. So it might looks like makes sense to define in non-square matrix, rectangular matrix, but the uniqueness it is broken. It will break uniqueness of matrix multiplication, and sometimes there is another concept to get inverse. It is called pseudo inverse matrix, and it can be non-square. It can be non-square matrix also, if you want to. If you are interested, what's the to do inverse? It usually write like this form. Really, maybe it was both. I do not remember in detail. I think it is identity. I don't know in detail, but I heard about that. There is this concept to find inverse matrix in non-square matrix. I will prove this theorem. Is it fine? It's proved by calculating from this. AB inverse means if we calculate AB, then it will be identity. From this, we will check if it is right. So we will calculate then that by associative rule we get identity. So this equality will satisfied because it all calculation in our definition of matrix multiplication or matrix multiplication. And to be before I start this class, I want to explain algebra. So we construct arithmetic in matrix, and finally we might need some powers of matrix to construct polynomial or construct algebra. And by accepting the matrix multiplication, it is very formal. It's very formal for square matrix, because to multiple time, then we need a square matrix. We need the concept of squares. So n powers of A, we denote it an, is A times A. I will skip times A dot A dot A n. There are n vectors of A. This is called it n powers of A. By using this, we get the we might be construct polynomial similar to polynomial. Let's see the example. If I give a polynomial and let it is a polynomial, then by substitute to x to A, we might denote this form, and it will give the matrix having same size with A. So this is called the polynomial of matrix. That matrix polynomial. And from this we can see we construct algebra, because polynomial is also algebra. We have plus and minus and multiplication. They are well defined. So let's see the property of these powers. It is very similar to scalar sense. I will assume A is invertible, and n is non-negative integer. Then the following statement makes sense. If multiply A s powers of A and t powers of a, it will be s plus t. I think you can calculate it by using this form, and it's very similar to scalar sense. So I will skip this problem. And the inverse is there is only one inverse. It has uniqueness. So the inverse, this inverse is original matrix. And for some n powers of A has inverse, it is similar to B. It will give A inverse is n powers. It means commutative, and by using this form does not depend on non-negative integer s and t. I will give s and t is just integer. And finally, the scalar multiplication is also distributed in metric sense. Let me check it. Then by calculating KA, it will be identity because it is inverse matrix. And by checking this, KA, the scalar is just multiplied for each vector, so it can be commutated with matrix multiplication, so it gives identity matrix.